The title of today's talk is How Zynga Scales Its Databases to Support Millions of Players. Let me start by introducing myself. My name is Sailesh Krishnamurthy. I'm General Manager for Aurora and MySQL databases at Amazon Web Services. And it's my honor to share the stage today with Wilson G., who's an architect at Zynga. Wilson, you're the most tenured, one of the most tenured engineers at Zynga. I've been there over 11 years. So he's clearly forgotten much more about building game services than I can ever hope to learn. Although I do know something about databases. So let me get started and sketch out today's talk for you guys. I'll start with talking about where and how modern online and mobile and internet games are run. Um, how you can run them on cloud architecture, specifically how you run them on AWS. And then I'll pass it on to Wilson to talk about how Zynga does it with Aurora in particular. And then I'll take back the baton and talk about how Aurora is architected, some of the particular cool innovations that have come in Aurora in the last 12 to 18 months, and where we're going. So with that said, let's start with running and building and operating modern online and mobile games. I was at a executive council of various gaming companies yesterday, and it was quite interesting to hear about how their architectures are. And clearly, the cloud is the new normal. There are many different imperatives for this. I don't need to tell you guys, but one of them, for instance, is when new games are coming on, you don't really know if they're going to be successful or not. And they may be much more successful than you dreamed, and unfortunately, every now and then they're a dud. And we see this with our customers. You have to be able to provision the amount of capacity and resources you need appropriately. And you don't want to pre-provision it way too much before you know how successful your game is. And in the off chance that it is not working out, you need to be able to bring it down. So the cloud gives you the flexibility to deploy your infrastructure in a particularly efficient and flexible fashion. But it's not just about the dollars and the profitability of your games. It's also how people actually come on board to games. What we see when we talk to our gaming customers is the need to be able to deal with things like flash mobs, sudden surges of players coming in. A game takes off as a viral hit. And for all of this, you want an architecture that is able to handle these surges of traffic, where you're able to dynamically provision capacity, and where you're able to scale up and down as you need. And we argue, of course, in our own self-serving fashion, that AWS is the best possible infrastructure for operating modern games. Now, a very critical part of gaming services is relational databases. They're used for various kinds of things: identity, authentication, payments, third-party payments with, say, other gaming platforms, A/B testing. We see so many different use cases. And especially MySQL is very commonly used in so many different game architectures and the backend services for gaming companies. AWS offers relational database services, RDS. And as part of RDS, we have our own database service called Aurora, which is a MySQL compatible database, which is about 5x faster than vanilla MySQL. So the typical architecture would look something like your application stack is running on multiple availability zones. An availability zone is at least one data center, and running onto an Aurora database service where the storage spans multiple data centers, multiple availability zones. So with this basic infrastructure that we're talking about, I think what I'd love to hear is more about how Zynga in particular runs their games, and take it from there.
Hi, everyone. I'm Wilson G. I'm an architect from Zynga under Central Technologies, and today I will talk about how to use Aurora in your gaming. A little overview here. I'll start describing a little bit about Zynga, the landscape of how our infrastructure is set up, our before Aurora state, some requirements we're looking for a relational database solution, why we chose Aurora in that case. I'll go over a few use cases within Zynga, and then I'll wrap up with a few lessons that we've encountered over the time and what we're planning to do next. So Zynga, what's Zynga? Zynga is a social mobile gaming company based in San Francisco with offices around the world. Our mission is to connect the world through games. And here is some games in our portfolio. We have quite a bit. We have poker, casino type games. We have words type games. We have slots, match 3, and here's just a couple of them on the slide. So now let's transition to how we set up our infrastructure at Zynga. So our games are either chosen to either decide to set up their own server infrastructure, or they decide to leverage services that Central Technology offers to them. Regardless, all the requests from either game clients or servers will go through our front gateway at api.zynga.com. api.zynga.com is responsible for authenticating the requests using either an external auth provider like Facebook or Apple Game Center or Google Play, verify that the tokens are valid, and then forward the requests downstream into our services, such as identities, messaging, payments, advertisement, track. And so the way our services are organized is that we built off of the microservice idea. And so each service is responsible for its own little small business use case with their own servers, their own cache, and their own databases. So what was it like before we chose to use Aurora? We actually had MySQL instances installed on EC2 instances within EC2. So while that was really good for our use cases and our workflows, it became a little costly when it comes to operations. So think about when a primary database goes down, we have to get a DBA come online, have them cut replication, promote a replica to become the new primary, rename that host, and then reestablish replication. And all that time could take 3 hours instead of a couple minutes that we want to narrow that down to. And that's a really important thing because our database is an important part of our game. So if the database is down, our players won't be able to play our games. So what do we need when we look at a solution? So live ops, as mentioned before, is really important. We want high availability. We want to be able to scale to billions of requests each day and also be MySQL compatible. So I'm going to go into each of these bullet points. So live operations. So with Aurora, it makes it super easy to fail over. It's automated for us. So whenever a primary goes offline, any readily available replica will then automatically come online and become the primary. You don't really have to change the cluster endpoint. It will just point to the new host. The amount of downtime is basically due to your DNS picking up the new host. It also makes it very simple and easy to spin up new instances as new replicas to test features, test audits, test changes in your schema, and be able to vertically upscale your instances. So if you're at a 2x, 4x, and you want to get to 8 or 16, you could just spin one up in the console, then perform a manual failover event, and now that bigger instance is now your primary database. Also on top of Aurora, there's also the CloudWatch alarms and graphs all set up there for you, so you could set up your alarms to message you and alert you whenever anything goes wrong. In terms of high availability, your data is replicated across all availability zones automatically by Aurora. So you have ideally 6 copies of that data across the 3 zones. And we have our primaries in one zone and our replicas in another zone. So it meets our high availability requirements. So I mentioned earlier that we had our MySQLs within EC2. So when we did a benchmark against Aurora, it scaled out perfectly for us. It performed the same way. So we felt comfortable moving to Aurora for that. And then MySQL compatibility was important because we do not want to change our application layer, rewrite our DAOs. So it's more seamless to change database engines just by flipping the switch. So now, who uses Aurora at Zynga? So we have several services within Central Technologies that uses Aurora. We also have a few game studios, Zynga Poker, and the With Friends network. So I'm gonna start going over some use cases, starting off with Zynga Identities. Identities is responsible for a single identity on a game, on a single device, and can map you to all your other devices that you've connected together via a Facebook Connect, for example. So our one database actually contains billions of identity chains. And a funny thing is, we're actually not using it as a relational database. We're using it as a key value store with a single key to a blob structure. We actually used DynamoDB as a previous iteration of that, and we switched over to Aurora after doing some benchmarking that there actually worked really well. And obviously the cost savings, we don't want to be managing the capacities for both reads and writes in Dynamo. And then a separate cluster is for our newest and greatest identities for our system. It's currently has hundreds of millions of accounts within it, and we're actually trying to scale that up to billions of records. We're just starting that process now. And so the next one would be Zynga Messaging. Messaging is responsible for sending notifications and stuff and messages to our users, either through push notifications, email, or Facebook notice. It was actually our first foray into Aurora. So we have a guest post on Amazon's blog detailing our process going into Aurora. The way we have our databases structured here is we have 3 separate clusters, one for the message templates, one for the email collected, and then one for push notifications. Facebook notifications don't run off of a database right now. One key important thing about here is that for our normal traffic, we have transactional sends, but on top of that, we also have mass marketing campaigns running throughout the day. So we'll see lots of spiky traffic behavior throughout the day here in San Francisco, and then it will be more idle throughout the night because we don't have any campaigns running at that time. Some key metrics here is we have hundreds of millions of emails and push notifications collecting in our database now. So now I'm going to switch over to Zynga Poker. Zynga Poker was our first game studio that moved into Aurora. It's a 10-year-old game. It's one of our oldest. We started off very simple with MySQL on bare metal, then we transitioned to MySQL in EC2, and now we're finally in Aurora. We started that process in February of 2016, and finally got there and completed in October of 2016. So it took about a 6-month process there. The way we have our databases organized is a mixture of simple monolithic type databases with a single instance with all the tables there. And then we'll have sharded databases, which would be more sharded on user-facing data. So we will have hand history within our monolithic and user account, number of your profile, things like that within the other sharded databases. Some cool metrics here is we have billions of rows and terabytes of data in all these databases, and there's millions of hands being played each day and trillions of chips exchanged within those players throughout the day. And then Words with Friends, another old title here at Zynga, follows suit, saw that poker moved to Aurora now, and so with Friends also moved. A little bit of context here is when I'm talking about Words, it's actually the entire With Friends network. So we have other games like Boggle and Crosswords that are driving off of the same server infrastructure. Same thing here is we have split between monolithic databases for general network level type data, and then our individual game and user data would be sharded. So things like your inventory, like your power-ups, your boosts are sharded there. Your game sessions that are active with your friends and all the moves that you make within those games. Another set of key metrics is that we have hundreds of millions of moves played each day with the with Friends network. So now I'm going to transition a little bit to some of the lessons that we've learned across the way. So I have a little table to the right showing Aurora's default values for max connection. And you could set it to a value of 16K as a max. We actually kind of ran into a problem here with Friends. We operate under a one connection per one Rails worker type model previously. And so we were getting pretty close to the max, and we were unable to scale our game any further. So we actually rolled back and then rolled forward after making some changes. So what we did was we set up some connection pooling and tried to limit and cut the number of connections down by 3x. We are using a third-party solution called Proxy SQL to do that for us. Simple, you just install that on your app server. It's responsible for proxying all the requests from Proxy SQL to Aurora, and your application will talk to Proxy SQL. Poker does the same thing. They use Proxy SQL after finding out about the software from Words with Friends. They observed that going across AZs for your read replicas, there's a threshold around 3-4K that somehow there's just unexpected latency there. So they're taking advantage of Proxy SQL to try to minimize their connections to the database. And then one other thing is we actually ran into a problem with the wait timeout that we set up for our previous MySQLs. We had it set to something really low and copied it over to Aurora. So just make sure that those values are tuned properly when you do a migration. Because of the inactivity, because the value was set to something very low, due to inactivity, sometimes the connections will get terminated on the server. And so reconnecting was a little high in terms of latency. So we also try to keep the application servers in the same AZ as your primary database and have the read replicas in other AZs within that same region. So like, for example, here, Words with Friends and Poker, we try to keep all our app servers in US West 2A with our primary database, and then we'll have our read replicas in 2B and 2C. Just to keep simple and reduce the latency between hops between AZs. A little different here is that Poker will actually send their reads to their read replicas, whereas Words will send reads and writes to the primary. In terms of archival, for Words with Friends, we typically just send down active game sessions to our game clients. Any completed game or abandoned game is not really sent down to the client. So we analyze our data, we try to archive them, and we're using S3 as that archival database right now. Just keep an eye out on your database. If you have data that is not really relevant, you could offload that, you could archive that into a separate database. And so I'm just going to wrap up here just to talk about what we're going to do next. In Central Tech, we still have several applications that are still running off of MySQL within EC2. It's time to evaluate all our services, see what makes sense. There's a couple that I know off the top of my head that makes good sense to move to Aurora, so we're going to plan to do that. And then addressing the whole topic about really spiky traffic, we want to evaluate a feature from Aurora for serverless, so you could dynamically upscale, downscale your capacity as you need them for your usage. And that's all I had for today. I'll hand it off back to Sailesh. Thank you.
Thanks, Wilson. That was fascinating. And it's quite a journey to go from first self-managed MySQL on, on bare metal on your own data center in your own colo, go to the cloud where you get the flexibility, but you're still managing the database on your own, and then eventually move to the managed database environment, and where there are multiple options. So before I get into Aurora and get into the details, I thought it's useful to provide some context. So about 10 years back, AWS announced something called RDS, or Relational Database Services. And that was really the first managed relational database that we offered, and I think probably industry-wide. And when we started RDS, it was a managed database service only for one database engine, for MySQL, for an open source database engine. So let me spend a few minutes talking about what this means, a managed database service. The core idea is we provide a set of web service API endpoints, and you can write an application or some kind of automation on your side to provision and monitor a database instance using this web service endpoint. So for instance, you have an API call that we provide that says create instance, create database instance, or create database cluster. We provide APIs to say take a backup, APIs to go and restore to a point in time. And so if you think about that, creating, provisioning, taking backups, doing restores, these are all what we call the control plane of the database. If you are running your database on your own, if you are operating your infrastructure on your own, you'd have to build all of this infrastructure, because you're not going to have, you don't want to, as Wilson said, when bad things happen, scramble to go and do things manually. You'd want to have leverage automatic failover for having managed failover. So these are all the services that you get from the control plane of a managed database service like RDS. And in fact, there are other things that we also provided initially as part of this. We would tune the database engine to the actual hardware. But if you look at where we were then, when we first launched RDS, this was still a world where we were running open source vanilla MySQL. But what we wanted to do, was go well beyond that. And in some levels, we went well beyond the initial version of RDS just by offering more choice. Again, Amazon is a retailer. We are happy to sell various different things. This is bought from Amazon, this clicker. And so we provide choice and provide many different database engines, MariaDB, different versions of MySQL, Postgres, and even commercial database engines from people like Microsoft and Oracle. We provide RDS SQL Server and RDS Oracle. But what we realized is we knew uniquely the challenges of building infrastructure at cloud scale. And so we wanted to build a database that was designed for the cloud. And Amazon Aurora is an enterprise database at an open source price point that's delivered as a managed service with a few key value propositions. The first is that you should have the speed, the availability, the durability characteristics of high-end commercial databases with the simplicity, the cost effectiveness of open source databases without predatory pricing, with drop-in compatibility with open source databases like MySQL and Postgres, with a really simple pay-as-you-go pricing that scales as your needs grow. So how do we go about building a service like this? If you think about it, the traditional open source database engines, which are very compelling, things like MySQL and Postgres, were not really designed for a cloud environment. So before we get into the details, let me talk about how what the pressures are when you take a database and move it to the cloud. If you really think about the core value proposition for database, you have a bunch of compute with a SQL query processor, a transaction subsystem, a buffer cache, writing to a bunch of disks. And really, databases do well when the I/O performance is good, and the I/O subsystem works well. And for 40 years, nothing changed in the database industry. To make databases perform well, you had to do two things. One, you had to reduce the number of I/Os. And two, you had to have a very high bandwidth pipe between your compute and your storage. And if you are running on your highly engineered colo environment, where you are able to have a bunch of fast disks, you could make that pipe between the database and the compute go well. But let's rewind back to where I started, with cloud being the new normal for mobile and gaming environments. In that kind of environment, what we actually observe is that compute and storage have very different life cycles. Compute instances or database instances are shut down. They may fail because of hardware failure. You may want to scale them up and scale them down, as Wilson talked about. You may have to fail over. You may want to have to scale out because you have a flash mob or you have a viral hit on your hands and you need additional read capacity. So if you think about what is going on in the cloud, it's very different from your old traditional environment. And in order to get that flexibility, we argue that in the cloud, you need to move from a world where compute and storage are tightly coupled to a world where they are decoupled. And then you need to replicate your storage across hopefully multiple data centers for availability and durability and resilience. So the key idea with Aurora that enabled a lot of the flexibility that we're talking about, that Wilson talks about, is decoupling storage from compute. And in order to do that, we built a storage subsystem on a fundamentally new architecture, on a scale-out distributed architecture. So this was a custom-designed storage service that was intended for OLTP database systems. If you think of a traditional storage service or even a network-attached cloud storage service like EBS, which is offered by AWS, Elastic Block Storage, you have an API where you read and write blocks, and the database engine actually does not know anything about how storage works. As far as the database is concerned, it's still 1979, where you wrote blocks and read blocks. So instead, in Aurora, what we have is a multi-tenant storage service that's scaled over thousands of storage nodes, thousands of servers in multiple data centers, in at least 3 data centers, 3 availability zones, where a storage volume for a given database is chopped into a bunch of 10 gigabyte chunks. And the database storage volume is essentially striped over this big infrastructure. The interface between the compute and the storage on the read side is very similar to how databases have always worked. If you have a page fault, if you're trying to find a page in the buffer cache and it's not there, we go to the storage service and we fetch the page. But on the write side, it's fundamentally different. On the write side, we never write full dirty pages, and instead we only write the deltas. So by writing the deltas and then replicating each portion of your data 6 ways, we're able to both get very high availability and resilience because we have 6 copies. We're able to survive not just random background noise failure in the cloud, but also catastrophic events like the loss of a data center because of a flood or rain or a snowstorm. And because we write only the deltas, we effectively end up writing about almost an order of magnitude less I/O on the wire. So that's kind of the core architecture, that decoupling compute from storage, and by writing far less I/O on the wire, lets us both scale, lets us handle, provide very high availability and durability, but also is a way in which we're able to deliver high performance. And so, in fact, in Aurora, compared to vanilla MySQL, we are able to offer write and read throughput, which is about 5x faster. And so, this slide is showing an experiment with, sysbench benchmark, where with vanilla MySQL, 5.6 or 5.7 or even 8.0, your write throughput will top out at around 25, 30,000 writes a second, DML operations a second, inserts, updates, deletes a second. And in Aurora, you can sustain up to 200,000 writes a second. Similarly, the read throughput would top out at little over 200,000 reads a second, whereas in Aurora you can write almost 700,000 you can have almost 700,000 reads a second. So in terms of throughput, you're going to see a substantial improvement in what you can handle on a given instance. So in terms of the latency of individual requests, that would be comparable. But when you can sustain so much throughput, again, I rewind back to where we started. How do you handle surges? How do you handle a sudden spike in the amount of activity? You need to have the headroom. You need to have a system that's scalable, that's able to take that kind of traffic bump, and that's what you get with Aurora. Now, there have been many things that's been said about Aurora. Before I get into some of the cool features, I want to take a step back and talk about the business side. Although Aurora is a relatively new service, been in operation about 3.5 years now, it's hugely successful. RDS itself is a very successful service with hundreds of thousands of customers. Aurora is the fastest growing service in AWS history, and that is when you compare with services like S3, EC2, and EBS. And from the time Aurora launched, it has been and remains the fastest growing service. And so that means if you sign up to use Aurora, you are signing up to use something that is highly strategic, that is doing very well, and is very successful. And so you're not taking risks like Wilson did 2 years back when we were still new. Moving on, I want to focus on a few very specific pieces of innovation. Wilson mentioned serverless Aurora. So let me talk a little bit about what serverless Aurora is. It's a new flavor of Aurora that we introduced last year. If you think about databases, we made it very easy to scale up and scale down by decoupling compute from storage. But when we look at our customers, we actually see a lot of people are still over-provisioning the database. They are still provisioning the database for peak capacity. Now, this is a little strange because we make it really easy to go up and go down. Now, it turns out that one reason why people still over-provision is that although it's easy to go up or go down, from the application's point of view, it's a real pain in the ass. Because when you go up or go down, when connections break, it actually introduces failure modes to applications. We have seen people whose applications don't do well in these failure modes. And a small hardware failure can result in a couple of hours of downtime just in how their application is dealing with failure. So the trick is not just about scaling up or down. That's easy to do. The trick is how do you scale up and scale down to save money while still not impacting your application. And that is the core value proposition of Aurora Serverless. The way we do it is we have a layer between the application and the database. That's the request router layer. Now, Wilson also talked about using something called Proxy SQL, which is an open source proxy, in order to handle things like connection pooling. So the request router that we're talking about here is a piece of infrastructure in the same vein. It's not written using Proxy SQL. But what it lets you do, using some very specific innovation on the Aurora side, is lets us seamlessly move connection state between different instances. So we have a warm pool of available database instances that are ready to go. And so if you hit a spike in your usage, we're able to take a database instance from that warm pool, add it to the Aurora cluster, fail over to that cluster, and as in the process of failing over, move the state of all the active connections. And all of this can be accomplished with the impact on the application just being something on the order of a few seconds, maybe 5 or 6 seconds, there's a blip. So it's a bit of a slowdown rather than actually snapping connections and restoring them. And on the way down, similarly, even if you have a connection pool, for instance, your connection, if your database is not active, it's the middle of the night or whatever, we will automatically sense that there is less activity, bring these instances down, scale them down automatically without impacting the application. The connection pool objects that are living in the middle tier of the application, they are continuing to live the same way, merely unaware that the actual database engine has moved to a completely different server. And the clients are completely not impacted by this. So the value proposition then is no application impact when scaling, a pay per second model. So rather than paying, for instances and, paying even when you don't use them, you're only going to pay for your database infrastructure when you need to. And this is really great for, things which are, I think, quite common in the gaming world, infrequently used, unpredictable workloads. And there was, I think, a tweet recently that I saw where there was someone who was running self-managed MySQL on EC2, and they moved their workload to Aurora, some test workload, and they talked about, I think, their daily EC2 bill went from $35 to, I don't know, 22 cents or something like that, right? Because that was the actual usage they needed. They were over provisioning. And from the Amazon perspective, our belief is we should make software and services easy to use, easy to consume, and we should not force customers to pay a lot of money. We think by reducing the price and making it easy to consume, we will open the aperture and have more people adopt our services. We think it works great for our customers, works great for us. So that's the first feature, Aurora Serverless. The second feature is, again, something which I think is going to be very exciting to the gaming community, the idea of a global database. Today, although we have regionalized infrastructure with many different availability zones and many different data centers, what the market is really asking for, especially what the gaming community is asking for, is the ability to deploy games to global audience. And so part of this is driven by concerns around disaster recovery. What happens if there is an earthquake? What happens if there's a flood? Now, in all of AWS's history, we've never lost a region. I don't believe we'll ever lose it, but it's a legitimate concern that many people have. The one aspect of the need for a global database is I want to make sure that the service still runs on another region, even if I have a truly catastrophic event. But the ask, I think, is well beyond just having the database, the data available in multiple regions in a globalized infrastructure. The real ask is that I want to have the application stack running in multiple regions. I want to have read latencies in any given region to be really low. I want to have the latest data available in any given region. And the holy grail is I really want to be able to write on all the regions. And that, I think, will open a whole vista of new kinds of gaming workloads. Role-playing games that are truly global, not just localized for a particular population. And now you want to do all of this. Again, the really hard part is to be able to do all of this without actually impacting your database performance. And now that is truly a hard challenge, a hard nut to crack. But we believe we've done it. In the first version of our global database, we are able to replicate at the storage level a database across multiple regions, where you're able to have an RPO, that is a replica lag between regions of about a second or less, while not impacting writes. So you're able to sustain that same 200,000 writes per second while still keeping the database up to no more than 1 second behind on any other region. And so this gives you truly cross-region disaster recovery. But we have much more ambitious plans beyond this. We've talked about this before. What we will be releasing is the ability to actually not just have global readers, but also write from many different regions. And I think this is going to be, we're very excited about this. We think this is going to be very compelling for the gaming community. One of the reasons why we're able to do all of this, if you just step back, is we fundamentally decouple storage from compute. And by decoupling storage from compute, we are able to do many different things. We're able to grow storage volumes as you need them. We're able to replicate storage across regions. But there are many other things that we're also able to do. So I'm only going to talk about one other cool piece. I can keep talking, but we all have to go and have dinner at some point. I'm going to talk about something called Backtrack. I don't know how many people have seen the XKCD comic called Little Bobby Tables. Anyone? All right, quite a few people. So it's really funny. You should search for XKCD and Little Bobby Tables, where someone has has the name of of their child enrolled in school records with effectively a SQL injection attack. Right? It's got some SQL statement, and the school administrators put in the child's name and wipe out their entire database because of the SQL injection attack. Anyway, so the point is you can lose data because of an error, an operational error or mistake, or because you didn't verify your SQL input, as in the case of little Bobby tables. So when things like that happen, how do you unwind quickly from a catastrophic scenario? Now, we do provide a lot of tools already for this. We provide the ability to do point-in-time restores. We provide backups. We provide a whole host of manageability. But each of these can take time. If I have to restore from a backup, I have to, our automation has to go copy the data from S3 or some other place and then go restore it and get the cache warm again. What we get to do instead is to bring the database back in time. It's almost like TiVo for your database. You can kind of rewind it to a point in time before the backtrack. You can move it back forward as you play around to try to figure out what is that precise point where you want to move to. And once you're there, you can continue start taking writes again. So it's a very useful tool when, to have in your repertoire when bad things happen. As all of us who have operated service know, bad things inevitably happen. They're just a matter of time. So the more tools we have at our disposal, the easier we can handle such situations. Now, there are other things we've done along the vein of backtrack. For instance, one other very interesting thing we have is something called copy on write, or a cloning functionality for our database. So you can say, you can have a live database and you can say, I want to create an instant clone of this. If I have a 10 terabyte database, creating a clone can take a lot of time normally because you're copying the data. But instead of doing a brute force copy, what the cloning operation of Aurora does is create an instant copy using a shallow copying technique called copy on write. So many different advantages. One is you get an instant clone without waiting. And two, you don't pay through your nose, because as long as the pages are shared, you only pay for it once. Now, as the two clones start taking writes, they will cleave, they will diverge. And as they diverge, you'll have individual pages that are copied during the writes. And as they get copied, you'll start paying for the additional usage. But cloning and backtracking together are very powerful. They give you tools not just for operational calamities, but they also give you a great way to handle test and dev instances, to take clones of your production workload and actually run run your deployments. You can imagine modern CI/CD pipelines where you're able to run this on actual real data. It's a challenge to do it as often. It's a way for, if you're running QA, you're running a bunch of QA activity that goes and takes the database forward. Backtrack can let you rewind back to a clean state in time, if you will, right? So kind of a meta transaction over your workload. So all of these features are only possible because of that original innovation of decoupling storage from compute. It is from that point that we're able to deliver so much, and why we're excited about the future. So that gets me more or less to the end of my story. We are going to open the stage up to questions. There's a lot of information about Aurora. There's a product page. There's management consoles that you can use on AWS. And we're here. We're happy to answer questions. So that's our story. Thank you.
Hi, this question is for Wilson. You mentioned that you set up alerting for your DBs, and I was wondering what kind of alerting tools you use.
Yeah, so we use cloud alarms to send notifications through SNS to topics that subscribe with API keys to things like PagerDuty, or notifications directly into channels within Slack. So we have an operations channel that gets all that information, and our on-calls will have PagerDuty alerts as well.
Thank you.
This question is also for Wilson. Could you elaborate on the performance gains when you moved the ZIS accounts from DynamoDB to Aurora?
So when I don't have the actual reports from the DBA, so they ran the benchmarking. But when we evaluated Dynamo as a key value versus Aurora as a key value, pretty much the gains were equivalent. They worked the same way. So we costed it out based off of pricing on Dynamo versus Aurora, and it made sense to make that switch over. So that's why we kind of have the that whole key value type of domain within a relational database.
Okay, thank you.
Hey, question for Wilson again. How hard was it for you guys to drop in your kind of legacy MySQL stuff into Aurora? And are there any kind of limitations compared to just having your own MySQL instances?
That's a good question. I personally did not work with the game studios to evaluate what they chose to do. For our Zys account database, that was built from the get-go with Aurora in mind. So there was no transition period there. Same for messaging. We basically rewrote a system completely and chose to use Aurora from the get-go.
Okay, thanks.
Hi. All of these cool features that you displayed, are they available for both MySQL and Postgres interface and in all availability regions?
So that's a good question. The question was, are these features available for MySQL and Postgres, and are they available for all regions? The short answer is no, but the longer answer is they will be. MySQL Aurora was released a little before Postgres Aurora, so there is some amount of catch-up there. So we are committed to having all of these features always on. There are some features that come out for Aurora Postgres first that will come to Aurora MySQL afterwards. And we'll certainly make this available in all regions, at least all regions that have at least 3 availability zones. There are still some regions where you don't have 3 availability zones. As of now, we are not releasing Aurora in those regions.
Okay, thank you.
Thanks.
Hello. I have a question for Wilson. You mentioned in regards to connection pool issue that you faced while transitioning to MySQL Aurora, and you mentioned that you had to make usage of proxy SQL. So was the connection pool set in proxy SQL or was it set in the application?
Yeah, so in this case, some of our older applications like Zynga Poker and Worst Friends, they're built in languages and frameworks that do not necessarily have connection pooling built into it. So we take advantage of proxy SQL, where each of those, I guess, are installed on the application server as a daemon, and it's responsible for listening to HTTP requests from your application to proxy SQL with the MySQL protocol, and then forwards that to Aurora. So the idea is you'll listen to more connections from your application, and then set up a smaller pool of connections between your proxy SQL and your Aurora databases.
Thanks.
Hi, I have a question for both, depending on where the answer is. In a case where you write to the master region and read from replica region, how do you handle the read after write consistent within the replication delay?
So the question was about read after write consistency when you write to the writer and then read from the reader. So that is the how this is handled even within a single region, and then there's a cross-region aspect of it. What we offer is snapshot isolation, full repeatable read semantics right now. And so on the reader, you're going to have a consistent view of the of the database. It's actually a point-in-time consistent view, but there is a lag. So what you actually end up seeing in the reader is a small lag. It's a point in time which is slightly behind. In practice, the point in time we see is the lag we see is about between 15 to 20 milliseconds. So for most people, that's a pragmatic decision. They're unlikely to have reads after writes, which is much beyond that. But for some people, that's not enough, or some people may see certain spikes for which they need to do a better job. And there are various kinds of solutions where you can keep track of a sequence number or transaction identifier, and or some kind of a cookie-like model where when you have a read right after your write, you can check, am I already caught up? And if I'm caught up, you let it go through, and otherwise I rerun it. So that's normally the advice we give people. That has worked out quite well. Having said that, we are considering different isolation levels. We are considering offering something where you don't have, this onus is not on, on the user. The tricky part is we want to do it without significantly impacting performance. We don't want to wait for that. So there is some work there.
Okay, so just to conclude, it's currently on the application side.
It is currently on the application.
Okay, thank you.
There are no more questions. I think that gets us to the end of the session. Thank you so much.